Yes, recording.
Yeah,
Thank you.
I think we should start now. So welcome everyone. I hope you have gained enough energy for the sessions in afternoon. So let's now start the second part of session 3. We have two speakers. The first one is Alexander Marjek from KU Leuven, Belgium. He's a second year PhD student. He works on the My Career IT project means. And yeah, I think that's all from my side. Alexander, the floor is yours.
Thank you. So good afternoon, everybody. I'm Alex. I'll be talking about millimeter wave Wi-Fi networks and the latency accumulation in their physical layers. Now, Ching already gave this away, so I'm a PhD student at KU Leuven, and I'm also a part of the DRAMCO research group. And as he mentioned, also the MINT European project, MSCA. Now, my main focus is millimeter wave communications, and within that, low latency for augmented reality and also broader extended reality use cases. I will start off with a bit of motivation on why low latency communications are important. And then I will go through the framework that has been designed and also a few examples on how to use it. First of all, when talking about low latency, it's important to know what low latency means in the first place. So how low should it be and who needs that low latency in the first place? Here I have an example of latency, the latency constraint for augmented reality users. And on the x-axis, you can see the head angular velocity of a user. That means the speed at which a user is rotating their head. Now, keep in mind that the user has a AR headset on their head. And on the y-axis, then we see the maximum allowed latency. So the faster the user is moving, the lower the allowed latency becomes. And in certain high mobility scenarios, that latency is as low as a single millisecond. Now, of course, augmented reality is not the only application that needs low latency. We have also, for example, vehicular communications that contribute a lot of potential use cases of potential applications such as traffic management or cooperative driving. Then you have also Industry 4.0 with cooperative robots that have a human in the loop that must avoid collisions and telesurgery, such as mentioned here. And all of these examples need a latency that is in the range of several milliseconds. Now, traditional approaches from the top down, so from the application or from the transport layer, are not perhaps sufficient anymore to achieve such low latency values. So therefore, it's beneficial to understand what goes on in the MAC and also the physical layer. Going from the bottom up, I started with the physical layer. Now, simulating the physical layer, for network simulations, we're actually quite spoiled for choice. There is, first of all, the NS3 network simulator, which is quite widespread. It has a big community. It also supports the 11AD standard, which is the millimeter wave Wi-Fi or WiGig. And it does an excellent job at MAC layer simulations. The problem is, however, it has a relatively abstract physical layer. So you cannot track the propagation of data through its physical layer. Then there are OpNet and YANS, which also do a similarly good job. But again, they come a bit short when we're talking about the physical layer. Then there is also Matlab, which everybody knows, and it is quite useful for substituting equipment which might cost tens of thousands of euros. And there were also some research endeavors in the past in providing an 11AD standard implementation in Matlab. However, the shortcoming again is no latency tracking in the physical layer. So what I did instead was I took Python and one of its packages, in this case, SymPy, the event-based simulation package, and based a simulation framework on top of that. It's all open source. It has a GPL license, so you can download it, you can work with it, and also redistribute it with any sort of modifications as you like. Now, to go first a bit more into the physical layer aspects and less the simulation framework. To start off, you first need to have a physical layer and a RX digital baseband in mind. That's because the TX digital baseband is already relatively well defined. You need to conform with certain wavefronts and with certain waveforms and certain modulation encoding schemes and such. But at the RX DBB, you have more freedom. In this case, I have decided to go with this particular implementation, which has frequency division equalization. You recognize that from the FFT and IFFT blocks. And in general, it looks like this. Now, the components that you see here are all implemented as blocks in the simulation framework. Blocks that you can redistribute and modify without much effort. So that means that if tomorrow we decide to simulate another RX DBB, it should be rather straightforward, since it is just a case of redistributing the blocks. Once you have your RX DBB in mind, it's then time to associate the components with their corresponding performance metrics. Now, the performance metrics in this case are derived from state-of-the-art literature on the specific component developments on the integrated circuits that were presented by the authors. And those give you a description of the latency for each component. The description of the latency is made up of two metrics. That's the throughput delay and the propagation delay, the data propagation delay. The throughput delay means that how fast, at what frequency a component can process the data. So let's say every nanosecond it can take a bit and process it. The propagation delay, however, is the delay from when a bit of data enters the component, it processes it, till it becomes available at the output. That's the propagation delay. And this is an example for the LDPC decoder, for which the two delays are dependent on the number of iterations and the number of cycles needed in each of the iterations. Here we have a really abstract representation of one of these blocks representing a component. Now, in the middle, we see the block itself. It doesn't do any specific data manipulation in the sense that it doesn't actually, say, decode or demap the data. It just trims it. So if we're talking about the decoder, which has some, so code words normally have some parity bit overhead, the decoder will remove that part of the overhead. The demapper will convert every symbol, so every just data unit, into multiple data units, such as a normal demapper would convert a symbol into bits. At the top of every block or every component lies its input buffer. Now, the input buffer is important because in the case that a component is a bottleneck, the data will start piling up in its input buffer. And the throughput delay is also connected to the input buffer because, as mentioned, that is the frequency at which the component can grab data from its input buffer and process it in parentheses and move it on to the next component. And the time in between, before it moves it onto the next component, it applies the data propagation delay, so the PD in this case. Then there is the data pipeline. That is the connection between an output of one component and the input of the succeeding component. So that's the connection to the input buffer of the next component. And every single component is represented by a block, has an input buffer, and has a data pipeline. Now the flag buffer or the flag pipeline is only associated with components that have some sort of dependency within the RxDBB. For example, this is the equalizer, which is dependent on the channel estimation or on the estimator. So the channel estimator first runs on the preamble on the channel equalization sequence, and when it's done, it outputs a positive flag buffer to the channel equalizer. And the channel equalizer, even if it has data coming into its input buffer already, it's not going to be able to run before it receives a positive input flag from the equalizer or from the estimator. Okay, speaking about time, now we've dealt with the simulated time, we also have the physical time. This is just a rough representation. And if I just make a quick example, imagine right now it's about 2 o'clock. You run a simulation, then it's 5 o'clock, 6 o'clock, 7 o'clock, the kids are at home, you need to go home and the simulation is still running. Now, in order to go home, you need to physically stop the simulation and repeat tomorrow, or at least pause it. However, to speed things up, instead the simulation framework uses multiprocessing, which means that a combination of the input parameters, those that influence a single simulation, so in this case, the modulation and coding scheme, the MCS, the payload length that you're transmitting, the demapping algorithm that you're using, which also has its corresponding delay functionality, and the maximum number of allowed decoding iterations. A combination of those 4 is run per process. And in that case, if a simulation would normally take up 8 hours, and I have my laptop here with 8 cores in it, it would take up roughly 1 hour. Now, if there is a laboratory, such as the one behind me, which has a lot of idle computers, right now nobody is using them, and during the night, during the Corona times especially, then you can also push the simulation onto those PCs, assuming there are 10 of these PCs, each and every one of them with 8 cores, then it takes roughly 5 minutes instead of 8 hours in total. And these nodes, these workers can be everything from a powerful server with hundreds of cores in it to a simple laptop or another PC in the laboratory. Lastly, let's look at a few examples. So here I have a representation of the traces or of the event monitoring in the physical layer. These bubbles represent events on the input buffers. The amount of them, the height, is then the amount of data units in the data buffer at a particular time instance. Now, there are 3 different events that can happen. A component can request data from its buffer, meaning, hey, I'm ready, I haven't got anything to process, so please, if you have any data, give me that data. Those are the bubbles at time 0, at the beginning that you see. The second event then is a put event, meaning the preceding component has offloaded some data into the input buffer of the succeeding block. And the third event is the block or the component has actually been granted access. It's the get event. Now, this is useful, this particular representation, for identifying bottlenecks. If you have a bottleneck, then typically you'll see high peaks in one of the components or in one of their input buffers. Here it seems like the cyan, the demapper, and the green, the descrambler, are 2 such components. However, that's not really the case. The high peaks in the demapper occur because the equalizer outputs entire data blocks, so 448 symbols at a time to the demapper, and it then needs to process them one after the other. Because the peaks are of equal height, that also means that the demapper is not an actual bottleneck. It manages to process the data just in time. If it was a little bit slower, then we would start to see the data piling up, and the demapper would therefore itself dictate the maximum achievable throughput of the physical layer. Secondly, we have the Scrambler here, which, as we can see, it's quite fast. So the decoder outputs entire data words to the Scrambler, and it manages to process them in almost no time at all. So the takeaway of that is it's fast, so it's not going to influence the total latency. Plus, it's very improbable to become a bottleneck. Now, lastly, we also see that not all of the bubbles appear at time 0. That's because they are flagged. Their input buffers are flagged. So meaning if we look at, again, the estimator and the equalizer, the channel estimator, once it's done processing its data, it will output a positive flag to the channel equalizer, and only after that can the channel equalizer request data from its input buffer. And this is the case for, so these particular traces that we are viewing are for payloads that are long 100 bytes. The MCS is index number 2, meaning BPSK modulation, and 50% of code rate of coding overhead. And the maximum number of allowed decoding iterations is 10. That's something that you typically see in a WiGig implementation. Moving on to the second example. Now, previously we zoomed in on the physical layer and on its components. This here is more of a black box study. It is like an end-to-end latency, but at the physical layer. So this is the latency from when data enters the physical layer at the transmitter, gets transmitted over the channel, until it exits at the receiver. So exits from the physical layer again. Here we have all of the MCSs, or almost all of them, the ones that were simulated in this case. And if I zoom into just 4 of them, so this is for BPSK modulation and for 4 different code rates. And all of the different code rates have a different amount of coding overhead. Now, what we can see here is that the 2 equal slopes of the code rate 0.5 and 5/8, those 2 slopes are equal, meaning that with a higher number of iterations, the time difference for transmitting a 100 byte long payload will remain roughly the same. There's only the so-called DC offset. However, that's not the case when comparing the 3 code rates below that one. Those are 5/8, 3/4, and 13/16. At the beginning, they start off from the same point. So if we're just conducting 1 iteration, all of them should have equal latency, meaning you would just go for the most robust one, of course. However, as time goes by, as you go for more iterations, they start diverging. And that means that with more iterations and also with more data, so now we're talking just about 100 bytes, it could also be 100 kilobytes, you get a higher time difference, a higher difference in the overall latency for the different code rates. And that's a particular thing that the simulation framework allows you to study. So to conclude, what the simulator does, it simulates IEEE 802.11 AD physical layer latency. There's a small bug in there. That's what we saw on the last 2 slides. Then it also supports latency probing and individual components, something which is otherwise not possible if you're conducting testbed measurements, because you can't just clip a communication module in half. Its weaknesses are that it does not support the broader Wi-Fi standards, so such as 11N or 11AC. And it currently conducts only simple data operations, which I mentioned trimming. It does throw away the redundant data as the data propagated through the physical layer. So all of the cyclic prefixes, coding overhead, and preambles, but it does not actually process that data. So that also brings me to the future work. One thing is including the data processing, or at least coupling it to an independent simulator that deals with bit errors and packet errors, and seeing how the latency depends on that amount of erroneous data in the transmission chain. And secondly, studying the latency in particular applications, because right now we were looking at 100 byte long payloads, which are just examples. So in practice, you might get different traces for different low latency applications, and that's where the simulation framework could really materialize. If you like the simulation framework, if you are into mmWave, then please do not be intimidated to reach out. I'm always open for further discussion, and you can also keep track of the MINT's European project and of Dramco, our research group, and see what's happening, what's the state-of-the-art research. Thank you for listening, and now if there are any questions, now is the time to ask.
Yeah, thank you very much, Alexander. Yeah, so are there any questions from the audience? Otherwise, you were talking about in future work how you want to include things like error and the data errors which you can come across. What would the influence be on the results you have now if you include that kind of things? Is it like too optimistic right now, your simulation, basically, about where potential bottlenecks might be, for example?
Mm-hmm. Right now, it's the most challenging thing is the end-to-end study. So if I have a Mac layer frame and I wish to observe the latency as it propagates through the physical layer, now I would just say, okay, go for the highest possible modulation scheme, because that has the least amount of overhead and the highest modulation. But in practice, if you have a noisy channel and then you look at that data at the other end, you might have a 50% chance of error. So really determining what's the ideal transmission parameter, if you have a threshold for the amount of errors that you can observe, and then optimize the latency.
Okay, yeah, thanks.
Yeah, thank you, Alexander. I think due to the time limitations, we need to move on to the next speaker. Thanks again
Thanks for the question
and the answers.